Hey everyone, and welcome to This Explainer. Today, we're taking a look at a really fascinating and honestly almost jarring snapshot of humanity as of August 2026. On the one hand, we're watching a world grappling with escalating geopolitical crises, intense kinetic warfare, and the immediate economic ripples those conflicts create. But simultaneously, we're witnessing some of the most incredible leaps in scientific innovation we've literally ever seen, from the microscopic scale of advanced silicon chips to the macroscopic scale of tracking impacts on the moon. It's a dual reality, really, human destruction and human ingenuity, both operating at maximum capacity at the exact same time.
Okay, let's dive into this. Here is our roadmap for today. 1. Escalating global conflicts. 2. Economic and trade ripples. 3. Silicon fiber optic breakthroughs. And 4. Tracking lunar impacts.
Section 1. Escalating global conflicts. Mapping the chaos.
Right now, three major hot zones are drawing intense international attention. First, the 2026 Iran war. This is heavily concentrated around the Strait of Hormuz, and we've seen a rapid exchange of vessel strikes and intense U.S. naval blockades. Second, the Russo-Ukrainian war continues to see significant military action, recently marked by record-breaking drone strikes reaching deep into capital cities. And finally, the Sudanese civil war is experiencing this complex mix of localized drone warfare in places like Khartoum and Darfur, happening right alongside major infrastructure efforts, like the rehabilitation of the Jebel Alia Dam. The scope of these overlapping conflicts is just vast.
To really understand the sheer scale of what we're seeing, consider this staggering number: 822. In mid-August, Ukrainian forces launched 822 drones at Russia. And according to Russian officials, this was the largest single Ukrainian drone attack launched all year.
The details of this historic assault really highlight how warfare is reaching far beyond traditional front lines. Of those 822 drones, over 600 were directed straight towards Moscow. The strikes resulted in at least 7 casualties and 39 injuries in the capital. The physical impact on infrastructure was also substantial. A massive Wildberries warehouse was completely destroyed. Plus, in a separate but coordinated effort, an additional drone strike hit an oil refinery in Nizhnekamsk, located in Tatarstan. This just perfectly illustrates the highly complex, long-range capabilities currently being deployed.
Section 2. Economic and trade ripples. The cost of conflict. In just the first 10 days of August, things moved incredibly fast on the global economic front. On day 1, LNG tankers, including a vessel carrying Qatari natural gas, were struck by projectiles in the Strait of Hormuz. And this chaos was compounded by simultaneous dual pirate hijackings reported off the coasts of Somalia and Yemen. By day 6, global trade policy shifted as the U.S. imposed sweeping new solar tariffs. By day 7, India announced the successful transit of 62 of its vessels out of the danger zone. And by day 10, the U.S. Central Command confirmed the mass redirection of dozens of Iran-linked vessels. It is a highly volatile maritime environment right now.
And that brings us to this specific figure, 55. This represents the 55 Iran-linked vessels that the United States Central Command has actively redirected since reinstating its naval blockade in July. It's an absolutely massive logistical operation designed to exert direct economic pressure on the region.
And this brilliantly illustrates the other side of that maritime coin. While 55 ships were blocked, 62 Indian vessels were safely escorted through the Strait of Hormuz under Operation Urja Suraksha. This operation, overseen by India's shipping minister, not only secured these vital cargo ships, but successfully repatriated over 4,000 seafarers safely. It really highlights the immense national resources being spent just to keep basic trade routes open.
But the high seas aren't the only place trade is being disrupted. Back on land, domestic policies are establishing firm price floors. On August 6th, President Trump issued a proclamation imposing significant new tariffs on polysilicon and solar products. So between naval blockades choking off shipping lanes and new tariffs completely altering the cost of green energy components, the whole global trade landscape is being rapidly reshaped.
Section 3. Silicon fiber optic breakthroughs, the microscopic marvels. Okay. Taking a deep breath from the geopolitical landscape, the scientific community is quietly changing the world. The star of this breakthrough is a material called germanosilicate. Think about the optical fiber cables that currently run our internet. They're made of this exceptionally pure glass that lets light travel for kilometers without losing its signal. What Caltech scientists have successfully done is take this exact same germanosilicate glass and found a way to print it directly onto tiny, standard silicon computer chips. So, instead of a long cable, they print the pathways in nanoscale spirals.
Now, what's really interesting here is the stark comparison between these two materials. The previous industry standard for optical chips was a material called silicon nitride. It worked okay, but it suffered from severe scattering loss, especially when trying to process visible light. But this new germanosilicate, because it has a relatively low melting point, scientists can put it in a furnace and reflow the surface. It melts just enough to become smooth down to the level of individual atoms. This atomic smoothness dramatically suppresses signal loss. And this isn't just a marginal upgrade. When we measure performance at visible wavelengths, the new germanosilicate platform beats the old silicon nitride record by a massive factor of 20. It's a true generational leap in how efficiently we can move light around a semiconductor. Now you might be wondering why this matters on a chip that is only 2 centimeters wide. Kellen Colbert, one of the lead authors of the study, sums it up perfectly. The longer light can circulate, the higher the performance of resulting devices can be. Every factor of 10 decrease in loss produces a factor of 100 improvement in coherence. Because the light is traveling in tiny spirals, if you prevent the light from scattering, it can effectively travel for meters, or even kilometers, inside a tiny ring resonator.
So, what is the ultimate takeaway here? What does this actually mean for us? Well, this breakthrough fundamentally lowers the energy cost of moving data. We're talking about vastly more efficient AI data center communications. It allows for ultra-precision optical clocks and gyroscopes. It paves the way for chip-scale atomic sensors, and it is a massive stepping stone for the advancement of quantum computing. It's a microscopic change with a macroscopic impact.
Section 4. Tracking lunar impacts. The macroscopic scale.
Let's move to the cosmos and see how this builds. On August 5, 2026, a discarded SpaceX Falcon 9 upper stage smashed directly into the lunar surface. This wasn't an attack, it was space debris. It's a real reminder of our increasingly crowded cosmos, especially as new initiatives like President Trump's Commercial First Space Directive push for a staggering 1,000 annual launches by 2030. This specific rocket was originally launched way back in January 2025 as part of the Firefly Blue Ghost 1 mission, and its upper stage had just been drifting through space ever since, until it finally met its end against the moon.
What's amazing here is how humanity worked together to track this. First, independent amateur astronomers around the world used public data to identify the object and predict its collision trajectory. Then, NASA's Planetary Defense Program jumped in, using this event as a live test to confirm their own methods for predicting hazardous object impacts. Finally, between August 11th and 12th, NASA's Lunar Reconnaissance Orbiter positioned itself perfectly to photograph the newly formed scar on the lunar surface.
The result of that crash? A crater 60 feet wide. The impact blasted bright and dark streaks of debris across the surrounding surface. The force was so immense that it actually excavated fresh, unweathered material that had been buried deep beneath the moon's exterior, giving scientists a brand new look at the moon's composition.
And so, the crucial point is this. We live in an era of breathtaking extremes. We are a species capable of mapping out a 60-foot crater on the moon, and we possess the genius to manipulate light down to the single atom on a tiny piece of glass. Yet we are simultaneously mired in devastating conflicts that sever supply lines and cost countless lives. It leaves us with a powerful question. As our technological brilliance continues to accelerate, how will we find the wisdom to navigate and resolve the escalating conflicts here on Earth? Thank you so much for joining me on this explainer.